algorithm, and we have understood that k-means clustering algorithm is having two main problems. One is specifying the k value and the initial cluster centers. Second most important is it will not take the outliers into a different position. It already consider outliers also for clustering, and it will make the clustering to be in a spherical shape where it includes outliers also. So it is not that much robust against outliers. We need some mechanisms to omit that outliers. One such mechanism we found is that DB scan clustering algorithm that is based on density, and another is actually called as the K-Medoids clustering algorithm. So the K-Medoids clustering algorithm says that you don't find in random initial, you don't fix the initial cluster center in from the first itself. Rather than you make it random and find the best initial cluster center called the medoid. The medoid is nothing but the dissimilarity between those points in the same cluster to the medoid will be as low as possible. Means that all the points in the cluster will be as close as possible to the medoid. So that is what actually the case. So here we are going to discuss starting from K means what are the efficient methods actually available and why such efficiency is required or effectiveness is required in clustering for which types of data. That's what we are going to discuss in this particular session. Yes. The first thing we are actually going to see is the spatial data mining kind, where in the spatial data mining, what actually it consists is, it will consist something called as the geometrical data, where, for example, I want to put a query in SQL or Mongo, right? Uh, all Walmart stores within 10 miles of UH, or all hotels near Krishnam Goyal. Like that, if I put a query, I need to extract the data. Similar data, the data is actually need to be clustered for hotels. If I need for any shops, it need to be clustered for shops. If I need for any electricians, then it need to be clustered for electricians and so on. When the data is actually having some geometrical meaning, then I will call that particular data as a spatial data. So I call that particular data as a spatial data. So the complexity of clustering will mainly increase with these kind of data, say spatial data or image oriented data, where the clustering process is not only based on those numerical items, we need to consider some extra items also. Those will include noise. Surely a huge kind of noise is applicable both in image data, I mean the video frame data also, and the spatial data analysis also. So we need some mechanisms to do that. Initially, we saw the partitioning algorithms are actually good enough to do the clustering effectively. But those partitioning algorithms say a k-mean is actually struggling with respect to outliers. So we strive to make that k-means to have some generalization where in each iteration of the k-mean, once I get the cluster center, I will do some mechanisms, I'll do some calculation to find the cost of having that particular 2 points or k points as a cluster centers. If the cost of having them as a cluster center is actually low than the other points, then I can fix those points as a good medoids. The medoid is nothing but the average dissimilarity of the objects from the cluster of the medoid should be as low as possible. If I have a point in the middle, then that will be served as a cluster center, and all other points should be closer to that particular point. Then that point I call it to the medoid point, which is having some smallest distance to all its neighbors. So these kinds of algorithm will be making sense that if a point is only 1 or 2 points is actually having a larger distance from the best medoid, then I can call those 1 or 2 points as some outlier point or a noise point. But the thing is, this k-medoid algorithm say if it is was trying to find something like this, these are actually not good medoids. Here, selecting this point or this point is not a good medoid. Why? Because instead of selecting these points, if I select some other better point, say like this point, then surely my distance, the dissimilarity to other points will be somewhat lower. So I have to repeat this procedure for every iteration I do. So K means by itself is an iterative algorithm wherein each iteration should be changing the cluster center. While K-medoids is also an iterative but a generalization way, where in each iteration it tries to find the best midpoint amongst the available points. It doesn't fix any 2 points or any k points as the cluster centers. It will try to identify all those points which are having a good possibility to be a midpoint. So I mean to identify that midpoint point. Points. I want to find the best 5 points from that best 5 midpoints from the 1,000 points. So which point will be a best midpoint? I have to check one by one. I have to check the dissimilarity, and I need to find the lowest dissimilarity point. That is a huge task, and surely k midpoints will not work for large data sets. So comes something called as partitioning around the mean, where instead of selecting the entire data once at a time, it will be first selecting the midpoint, and based on that midpoint, one by one the point will be occurred over those midpoints. I'll be finding some dense point, and for the dense point is nothing but it is having more closer points around it. I'll be checking that point, say OI. I'll be selecting that point, say OI, then I want to check whether the new point Oj is going to belong to Oi or not. So this is what the case in PIM. So PIM says that you just fix any one point as Oi, that is the marked in red color that I consider as midpoint. One then, if for this midpoint the neighbor should be identified. So when I want to identify the neighbor and what is the procedure is, I can use any type of distance metric, say Euclidean, Manhattan, or rho, or any other distance metric I can use, and that distance should be as low as possible to that OI. So if there is a distance OJ to OI is actually equal to minimum distance for OJ to already existing node to OI. OE is nothing but already OE is actually existing in the cluster of OI. So if it is actually minimum, then it is actually equal to the minimum distance. Then it's very good. You can directly add OJ also to the group. If else, you should actually go for the next point, say OH. You replace OJ with OH. Now again try with OH and see what is the distance that OH is having with respect to OI compared to already existing points in OI group. Right? I repeat again, what is the main thing about K-medoids? They are resilient to outliers. So what will actually happen in K-medoids? I'll be trying to find some point which is actually having some denser structure around it. If I take the distance from the medoid point to all other points in the same cluster, then the distance to each other points will be as small as possible. So the dissimilarity to all other points will be as small as possible. So that I call it as the medoid point. But the problem with k-medoids is if it is a very large data set, say there are 1,000 points in the data set, and I want to select 5 medoids. I want to have fixed k value as 5. Then I want to select 5 medoids from the 1,000 points. Surely selecting 5 points out of those 1,000 points is highly complex because for every possibilities I need to find the dissimilarity measure, and I need to find the 5 combination of points which is having the lowest dissimilarity amongst that 1,000 combinations. So it is highly complex. That is, each iteration of k-means need to be done again and again with checking the dissimilarity. So k-medoids will not work well when the data set is very large. One of the application or one of the variety of k-medoids is PAM, partitioning around medoids. So what is that partitioning around medoids is nothing but I need to identify k representative objects, that is how many clusters you want, and for those k representative objects I name that they are going to be the medoids. Initially itself I'm saying they are the medoids. There are some procedures for selecting that. So instead of selecting medoid again and again, starting itself I'm fixing they are going to be some medoids. How I'm selecting? That particular points will be having a dense structure in the cluster. So I can select that particular point. That is, they are actually the most centrally located object within the cluster. I'll be selecting as midpoint. See, the most centrally. I'm not saying accurate central. The most central point I'll be selecting as a midpoint point. Then what I make, I consider that the point is going to be the OI point. For OI, I want to take the other points which I actually going to be joining this OI group. So assume that OI is already having some points, say OE is there already present. Now we need to identify whether the new point oj is also going to the group of oi or not. So what will we have to do? So I'll be taking some distance metric, say Euclidean distance metric or Manhattan distance metric or row distance metric. I'll be taking that, and I'll be using that distance metric to see what is the distance from OJ to OI. If the distance from OJ to OI is equal to the minimum distance from OJ to the existing points, already existing points in the group of OI. If there is minimum, then okay, I can join them in the group, because OE are nothing but the points which are already in the group of OI. So if the OJ is actually closer to them, then surely, if since they are in the group of OI, OJ can also be in the group of OI. Here's what I have to do. I should eliminate OJ to be in the part of the OI group. I should include OH group, right? The thing is, now there are two things involved here. First one is, though you have fixed the medoid to be the most centrally located point, the cost of actually fixing a new point inside the cluster and the cost of swapping from one point to another point, everything need to be fixed very clearly. Say for example, here I was actually choosing a point, say OJ, and I was trying to fit OJ to the cluster OI. So that involves some cost. And I need to swap OH and OJ also. That also involves some cost. So these swapping cost and assigning to the and selecting that particular point to the cluster, everything involves cost. So that cost also to be managed to make it efficient, right? So see how the PAM actually looks. First, initially you have to select some k medoids, and for that arbitrarily selected medoids that we call as a representative objects, and these representative objects are nothing but the most centrally located point in the data sample, most centrally located data sample. I call it as a k representative objects or k medoids, and for those k medoids I'll be selecting the cost of including the new point, say OH, to the existing group, say OI. So new point is actually coming from OH, that is need to be added to OI. That is, I'll be taking the cost. We know what is the cost. Cost is nothing but those swapping cost and the cost of finding the similarities and then putting OH into OI. The total cost, I say. Total cost of putting H to the I group. So I will be computing that, and I'll be selecting the pair OI and OH to be included in the group, provided that if any already existing point is present in the group of OI is also closer to OH. Say for example, so these scribblings are visible now.
Yes, sir.
So assume that I'm having a point, say OI, and there is already existing point, say OE. They are actually in a group. They are actually forming in a group. Now a new point, say OH, is going to come, and OI being a most centrally located point, they are actually selected as a representative object. So now they are actually having some minimal distance, so only they are actually in the same cluster. Now initially I'll be finding a distance to OI to OH, and this distance should be minimal to the distance from OE to OH at least. Why? Because if OE and OH are very closer, since OE is actually present in OA, then OH can also be present in OA. That logic. Since OE is actually closer to OH, and OE is present in the OI group, I can also include OH also to the OI group. So that is actually the logic here. So that's why I take the minimum distance. At least for any one of the items in OE, it is having a closer relation or not. If it is having, then I can include them. And I'll be calculating the difference of TC. So difference is nothing but if for the previous node, say it is having giving the cost is say 15, the total cost is 15, and for the newly entered point, say another point in OH1 is there, that is giving 15. For OH2, assume that the cost is 18, and for the, if you take the difference of the total cost 15 minus 18, you'll be getting a negative cost, means that your new cost is actually higher than the already existing things. So the thing is, it is having some negative things you have to replace. you don't take that particular point as a good point because they are actually having some higher distance. So what you should do, you should replace the values. Similarly, you have to go again and again, and you need to find the best medoid again, and you have to fit it into the representative object. This is actually the case, and the complexity of this is actually found to be we go of k into n minus k the whole squared for every iteration. So this is an iterative process, and it will converge when both of them are when any two consecutive iteration is having a same cluster pattern. So the total complexity is nothing but a big O of k into n minus k the whole square. So it is actually good for small data sets. Some like number of sample is equal to 100 and the k value equal to 5. For these cases, PAM is actually working good. But PAM may not work good if the data set size is very large. Right? Say for example, if you are increasing the size to around say 1000 or something, purely PAM will not work good. So that we go for the new kind of clustering, say clustering large applications, shortly called as Clara clustering. So what is Clara clustering? Clara actually takes the same thing what I said by k medoids. That is, it is going to identify the best medoid. But what k medoids and the PAM says, you need to identify out of 1000 samples, you need to find the best 5 medoids. That's what is said by the k medoids and the PAM. Now, what Clara says is why you are taking all the 1000 points. Instead of taking all the 1000 points, you take random samples out of those 1000. Say you take 100 samples out of that 1000. Out of that 100, you find the best 5 medoid. Since you are randomly selecting points, there will not be any bias. And out of the 100, selecting 5 is also not a best, there will not be a high complexity task also. So instead of selecting the best 5 medoids from 1000 points, you select best 5 medoids from 100 samples of 1000. So you just in the local sample say 100, you are going to select only 5 medoids. So that will be easy to do. And if you want that to be repeated, you can have several number of different samples and several different medoids also. So that is actually the parallelization involved by Clara, and this Clara clustering works good. And some more variation also came when randomization is coming into play. Instead of just having clustering large applications, it has also included like clustering large applications based on some randomized search. There we combine both PAM as well as Clara. Say for example, we construct a graph where I'm having something like a group, say S1, S2, S3, S4, like that. I have a very various kind of groups. There is actually a global group of points where there are 1000 points located, and out of those 1000 points, several samples will be taken. So assume that this is a sample, say 1000, and for this 1000 samples, I'll be selecting randomly 100 samples for everything. So here I'll be selecting 100. Here I'll be selecting some randomly 100. So here I'll be selecting some random 100, and here I'll be selecting some random 100, and so on. I can increase this and go. So this is where PAM comes. I'm partitioning everything. So out of this 100, I'll be selecting the best 5 medoids, the best k medoids. Whatever k is given to you, you select that k and you assign it. If you directly select the k from here, then it is k medoid, and it is a PAM. But you make it actually like this. And there is also a criterion that some point may be actually present both in S1 and S2. In the parent also some points can be there. But the child may not have the points repeated. So you'll have the medoids being selected among this. And out of these, you'll be having the medoids being selected one by one. Here you'll be selecting some k medoids, here you'll be selecting some k medoids, and so on. So the medoid is nothing but the best cluster center you can actually fix. Why we are actually very strong on selecting the cluster center is nothing but only when the cluster center is correct, then only the clustering will be strong. Otherwise, the clustering will not be strong. So only we are actually that much prominent to select the best cluster center. And the k-means also, the main problem with k-means also is the same. K-means says that I'm taking the mean point as a uh, I'll be taking some mean and I'll be assigning that as the cluster center. That point may not be in the database itself. That is actually the mistake done by k-means. So this particular thing, what is actually they are saying is the point what you select should be in the data sample, and then only it should be taken for the best meroids also. So we are actually selecting that kind of points. So once a k meroid is found, then I'll be fine out of those different sample, which sample is having the best dissimilarity measure. I'll be taking and I'll be considering it into the clustering process, right? Now I'll show you the block diagram and how the Clarence actually works. So this Clarence process will be actually a sequential process. I'll explain you very keenly to understand that. So this will algorithm requires two things. One is num local, nothing but number of iterations I have to do for completing this particular process. That is actually num local. Next, I'll be having something called as max neighbors. Max neighbors is nothing but maximum number of neighbors that is required to form the particular cluster. So these two things. One is num local. Num local is nothing but the amount of iterations I have to do to finish the task, and neighbors is nothing but how many number of points should be there as neighbors to form a cluster. Next, I'll be fixing an iteration. That iteration will be say, starting from 1. So I'll be fixing it I equals 1. And I'll be fixing something called as the minimum cost. So I need to make the best cost node. So initially minimum cost is set to be a very high number, that is infinity. So when I traverse it again, I'll be getting the minimum cost to somewhat lower number. For initial case, I'm getting to be some highest number, say infinity, and I need to select the best node. Initially, I don't have any. The best node is nothing but the best medoid. Initially, I didn't select any medoid, so I select it to be -1. Next, I fix something called as the random points. What is my k value? So for now, k random data points which are selected, I'll be selecting some random meroid points. Randomly, I'll selecting k meroids, and that k meroid should be considered for evaluation. And for those k meroids selected, I'll be finding the distance from that meroid point to all other points in the data set. I'll be finding it, right? After this, a new loop will start. That is nothing but the J loop. So far, what is happened? I fixed the 4 items. That is num local, number of iteration, maximum neighbors to form a cluster, minimum cost that is fixed to infinity, and best meroid. I didn't select any best meroid, so -1. And randomly, I have selected some k meroids, and I'm going to a new iteration. That iteration starts from j equals 1. Next, from the randomly selected meroid, select any one and compare it to that all the data points in the data set. So you compare from the randomly selected member in the data set. From the point in the data set is going to be yes, and I have one meroid also. Compare it with them. If the replacement of the candidate data point is actually having a lower total cost. If I was selecting this and I was replacing the existing random meroid by this new point, if the total cost is actually somewhat lower for S rather than the current meroid, then you replace the meroid by the new point in the data set. This is as a new most important MCQ. When you have to replace the current meroid, if the newly selected data point is exhibiting a total cost less than the existing meroid, then you can actually replace the randomly selected meroid by the new point in the data sample, and I'll be assigning it as the current, and I'll be going to j equal 1. So this iteration will continue, and j will be equal to j plus plus and so on. So I will again select a new point. Once it is not satisfied, it will come to j plus plus. So means that if it is j plus plus, it means that the current meroid is there, and that current meroid, the newly selected point will become a group. They will form a group. So how many members should be there to form a group? We have given something called as maximum neighbors. So I want to fix until j is actually less than max neighbors. I have to proceed with randomly selecting another data points and so on. Yes, what I can actually do, and if the total cost is less than the minimum cost, the best node is updated as the current node, right? If else, what I can actually do, the current node will not be fixed. I'll be again going for selecting another data point, and I'll be doing the same process again and again. Once the best node is selected, I'll be incrementing the first for loop, and I'll be going to the num local again. One iteration is completed. In this iteration, I have kept this particular point as a current medoid and the best medoid also. And that process will be going for, if I want to k medoids, I'll be trying to find those k medoids, and then I'll be finding the best node, best combination of node I'll be finding, and then I'll be coming out, right? I'll be explaining it again. So this flow chart will be having many small MCQs inside. I'll be explaining you it and somewhat more time. The minimum cast node I have to select. Initially, I fix the min cast to be the infinity, the largest number, and the subsequent things I'll try to find the minimum thing. And what is the best node? The best medoid possible in the current iteration. Initially, what I'll be doing, I'll be selecting randomly. I'll be selecting some data points as a medoid, because according to k medoid thing, you have to you have to find a medoid for each iteration. Else, in Clara, what they are actually saying, you fix the most central point as a medoid. So randomly I'm selecting the most central point as a medoid, and I coming to the next iteration where j equals 1. Here what I'm selecting, from the data set, any one point randomly I was selecting, and that data point should be compared to the first medoid what is actually being selected. If the total cost of forming a cluster with respect to S, the new point taken from the data sample, is less than the cost created by the medoid, then what I can actually do, I can reject this medoid and I can include S to the data sample as the new medoid. So here I can update it as new medoid. Else what I can do, then else I can include that in any one of the clusters and I can proceed. Here in the, if it is actually included, then subsequently I'll be trying for all the data points to form a better medoid. Next I'll be coming here, but if j is less than the max neighbor also, I should again go, I need to find for a single cluster to form, assume that the max neighbor is going to be some 5. So at least 5 neighbors are actually required. So I'll be repeating the iteration until 5 neighbors are formed. Next, I'll be finding what is the cost for find minimum cost required for that particular medoid. If the total cost is less than the minimum cost, then I can directly select that particular medoid as the best medoid. Like that, I have to find several different. I have randomly selected say k different medoids, and I need to run all the k different medoids for this iteration, the inner for loop iteration, and I have to select the best medoid out, and then I should return the best medoid. And for this best meat, I'd say here the number of iteration that can form for the typical data set given to this flowchart is 2, and the max neighbors can be around 1.25 percentage of k into n minus k. So what is k into n minus k is nothing but in the previous PAM, if you have seen, PAM has a complexity of big O of k into n minus k the whole squared. But here the complexity of running it, say it is going to be 1.25 percentage of k into n minus k for the data samples of 250. So surely Clarence can be using some randomized search. Randomly it is picking some points and it is finding the best medoid. So surely it can handle even a very large data set much efficiently. That is with respect to them. Now if you compare Clarence with Clara, the relative distance, the relative average distance is nothing but it should be as low as possible. For example, if the relative average distance is actually very large, then it means that clusters are not formed correctly because they are highly splitted with more diverse. If they are more converged, then it means that they are actually very close, very good clusters are found like that. If you see here, for Clarence it is actually very close. Clarence is actually very close to the origin, and the relative average distance is very low compared to other partition averaging methods. That in Clarence, I can have the thing on this one axis itself. Whereas for others, it is actually somewhat relatively higher. And if you take the runtime also, the runtime of PAM is actually increasing iteratively, but Clarence, as the iteration proceeds, it is actually converging in the lowest level itself. Because I'm not going to check all the data points, I was going to select some random data points only. So my result may not be accurate as such, but I can find as good a number of medoids possible. So you take runtime also into consideration. You take the relative average distance also in consideration. The best can be Clarence when compared to the PAM method. Next comes the spatial and non-spatial dominant Clarence. So you take either, now we have discussed only the spatial things where a data set involving some geometry will be taken into consideration for clustering. Say for example, hotels near me, or jewelry shops near me, universities near me, like that. If I say something, then it is actually with respect to some spatial distances. But if it is a non-spatial data set, if it is having some two-dimensional criteria, then what will actually happen? Your data set will be like some color and diameters, and those colors and diameters can be grouped into some other things like color. This reddish, yellowish, bluish, and all can be grouped as small, large. Like that, I can actually make them to form some clusters, right? What will actually happen is, if you are actually using SQL query, this Clarence clustering is not much required for a non-spatial kind of data set. So because non-spatial kind of data set is actually 2D related, and it may not require that much efficiency to run it in randomized way and all. As I already said, either you take some genetic algorithm, or either you take parallels with MongoDB data set, or either you take this Clarence data set. When they are higher level, if you supply small data items to them, they will not put their efficiency over those kind of data. So clearly that those are actually not required. For that, we actually make something called as a parameter, say Silhouette coefficient. What is Silhouette coefficient is nothing but it determines how much weightage it is there for OJ to get belong to a particular cluster. Because if there are OJ and OI, in how much percentage I can say that OJ and OI can be in the same cluster. That is actually said by something called as Silhouette coefficient, which can be in the range between -1 and +1. One indicates that high degree of membership is available, and -1 denotes the opposite. That is, no, it cannot be in the same cluster. And if you see the range of Silhouette width, right? If it is actually between 0.71 and 1, it means that they are very strong clusters and they can be together. And 0.51 to 0.70, we can say that it is going to be a reasonable cluster. And from 0.26 to 0.5, we can say it as a weak cluster or an artificial cluster. That is, manually we are trying to make them into the same cluster. If it is less than or equal to 0.25, then surely they cannot form a cluster and they cannot be taken into consideration. So these Silhouette coefficients are actually available. When we train this in our ML code, we can easily get what is the Silhouette coefficient for the particular cluster. We can easily find. Say for example, in the previous laboratory session, we have seen the agglomeratory clustering as well as the k-means clustering. For those clustering, we have fixed, based on the elbow method, we fixed the k value as pi. For each of the k's, we can find what is the Silhouette coefficient. Whether they are strong clusters or weak clusters, you can find. So the Silhouette is actually one of the method which actually says us the strength of the particular cluster being formed. And again comes the spatial distance and non-spatial data set concerns. So the second thing is actually working on tuples like that. But the first thing is actually based on the geometrical oriented thing. You can also come down from the spatial data to a non-spatial data. You can convert those geometry also to a non-spatial data. But ultimately, what will happen is the underlying query matters a lot. Whatever you do, the query matters a lot. If you take any data set or if you want to put Clarans, Clara, whatever data set you use, but the ultimate is what is the SQL query or MongoDB query you use. That is what actually matters a lot. If you take SD Clarans or NSD Clarans, the thing is, what is the SQL query you write? That actually matters a lot. If your SQL query is actually touching the nose from the back end, then surely the Clarence and all will not work. So it matters that starting from the query what you write when you search a particular cluster. Like if the question is posed like finding the nearest hotels to me, if your clustering can be done faster based on using Clarence. But if your query is not that much good to fetch an efficient hotel, then surely Clarence doesn't matter for it. So this is actually with respect to that. And the whole I can summarize that your partition based algorithms include k-means, k-medoids. So in partition based methods we have seen k-means is not good enough when the data set is having outliers. But k-means is very good when the data set is having large number of samples. K-medites coming to here, they can work well with outliers, they can remove the outliers, but the K-medites and PAN will not work when the data set is having more large number of samples. So I want outliers also to be removed. I want it to work with large samples also. So I go for something called as Clara and CLARANS. Clara is nothing but I want to cluster with respect to some randomization techniques. So that randomization will appear that I, instead of searching for medites, I'll fix some centrally available cluster points as medites and I'll be working towards those particular points. That is with respect to the Clarence, right?